Hi, so good afternoon or good lunchtime. And today we're going to hear from Tom Blyer and learn about earthquake prediction and what's possible today. Just wanted to say a few words about Tom. Tom, I guess, has been interested in this for a long time, doing work in earthquake prediction 20 years ago or so in high schools. 30. And but his profession is being a rocket scientist. And then around 1999, he went to Stellar Solutions to be a rocket scientist, but quickly they decided that earthquake prediction would be a great endeavor for them, and they started up a humanitarian research project at Stellar, and Tom heads that up now. So let's find out more about earthquakes and whether we can predict them. Take it away, Tom.
Thanks. I appreciate the opportunity to come to talk to the Google audience. One of the things that I'd like to open with is that this is a bit of a career change for me, working in aerospace and satellite system engineering for about 30 or 40 years. This is one of these things where you have a passion about just to learn about something else, and this passion has evolved into this project. And so we're going to tell you about the project today and hopefully give you some insights into what's going on. So our company is called Stellar Solutions. The project is called QuakeFinder. It's been going on now for about 13 years. And what we're doing is to develop a way of forecasting earthquakes on the order of 2 weeks to a couple of days before the earthquake. So this is not the P-wave, S-wave earthquake warning system that you may have read about in the last week or so. That's a system that works on seismometers actually picking up the earthquake that's already started and then sort of going close by and warning people that the earthquake has started and it's coming towards you. So you get anywhere from 0 seconds to maybe about 30 seconds of warning. And eventually they hope to have that work into a cell phone alarm system. But if you happen to be in the wrong place at the wrong time, like in the BART tube going underneath the San Francisco Bay or next to a gasoline storage facility, that may not be good enough to protect you. So we think there's a purpose in having a short-term earthquake forecasting system. Some of the people that are helping us here, in addition to Stellar Solutions and NASA, we've got some universities in Taiwan, Greece, and Peru, as well as the University of Colorado. So I'd like to acknowledge those folks. So what about this earthquake forecasting? It's a tough problem. It's not something that's been solved, as you may realize. If you look on the lower left of the screen there, you can see that weather forecasting took a quantum jump when they developed geosynchronous weather satellites that could watch the storm coming into like the Gulf of Mexico or wherever, and supercomputers to do modeling of the way weather actually propagates and moves. Likewise, tornadoes took a quantum jump forward when they developed Doppler radar. So instead of just listening for or having eyewitness reports, they can actually see the funnel cloud starting to spin up and actually provide a warning of a few minutes before the cloud actually touches ground. Volcanoes are a little bit harder, but they're coming along. You can actually watch the volcanic cone inflate as the magma starts moving up into a chamber. Interferometric radio SAR, synthetic aperture radar, is a way of monitoring that from space, as well as GPS on the ground. So you can watch gases, you can watch inflation, and you can get a sense of when the volcano is going to blow. Landslides are kind of similar. You can watch the rain gauges, you know the topographic area and what areas are ready to go. But the problem is you come back to earthquakes and nobody's making earthquake forecasts, at least not reliable ones up to now. So if you look at how man has approached this problem from, around the year 100 AD, the Chinese in the upper left-hand corner there came up with an interesting little thing. It looks like a vase of some sort, but there's a pendulum inside of it. And as the earthquake waves come through the area, this pendulum starts wagging back and forth, knocks a steel ball out of the dragon's mouth, and it falls into a little toad on the periphery of this thing. So not only can they record the fact that there was an earthquake happening, but they can actually get a sense of which direction it was coming from, depending on which ball goes into which side of the array of toads there. If you fast forward a little bit more towards today, after we discovered, or after the scientists have discovered the ring of fire and plate tectonics, obviously there's a large amount of earthquake activity going around. So people have been putting in seismometers for years and years to discover where the earthquake happened and how big it was. But they're also looking for patterns of earthquakes, something that might show a cluster of magnitude 4s or 3s before a very large magnitude 7. Unfortunately, that hasn't worked out very well, and there really hasn't been any good forecast made. More recently, GPS and LIDAR, or laser ranging systems, were instituted and placed in certain areas along the fault, so you can measure the amount of stress that's being built up and strain that's being built up along the fault. But even that hasn't really turned out to be a good forecaster of earthquakes. And finally, on the right side there, interferometric synthetic aperture radar. You can take a picture of the ground with a radar imaging system, and then a week, a month, a year later, take a picture from the exact same spot in space as the satellite finally comes around to the same area. Take a picture, overlay the two images, and you can develop these interferometric rings that tell you essentially how many centimeters the ground has moved. So if you take a picture before an earthquake and one after, you get these very wild ring-looking patterns that sort of look like a butterfly. Unfortunately, it hasn't shown that it shows much deflection before the earthquake. So even that has not worked out too well. So we decided to do something different. Everybody else was doing mechanical things, all of these things I just talked about. We decided to look at it orthogonally. We wanted to look at electromagnetic monitoring. And we were interested to know if there was any physics going on at the hypocenter that might generate some kind of an electrical signal. So the thing that got me started in this whole thing was a briefing that a USGS scientist gave back in 1970s, and it was called Earthquake Lights. Now, anecdotally, there's been stories all over history about lights flashing in the sky prior to and during earthquakes. But this guy actually had pictures of a place in Japan in 1967 to 69 where there was a flurry of earthquakes, and he started taking pictures at night of these glowing patterns showing up in the sky, sometimes on cloudless nights where there's no lightning going on. And more recently, we had a collaborator down at Peru, and the university down there, the Catholic University, had a surveillance camera looking out into the harbor. So this, oops, there we go. So down on the bottom there, we're looking at this surveillance camera. It's a little distorted, but you can see some flashes of light, and where we're looking is out towards the harbor, towards the ocean, essentially. The camera starts moving, it sees one flash of light, sees a second one. That represents the P wave and the S wave going through Lima from an earthquake that was a magnitude 8, about 150 miles south of there. So all along the coast of Peru, these lights were flashing as the P wave and S wave came along. There was actually 2 earthquakes that happened here. The second one, you can start to see it moving the camera a little bit. That also had a P wave and S wave going through Lima. And again, the camera will start to pick that up, hopefully in a few seconds here. And it represents a major change in stress in the Earth's crust that's causing this. And as the camera is starting to move, you'll see in that black area again a flash of light. There it goes. That's the P wave going through. And finally, the S wave coming through, showing that there's some electrical activity that's really being generated as the crust is being bent and torqued. When the researchers saw this, a lot of people said, oh, that's just power lines, arcing back and forth. And he thought, it didn't look like that. It looked like it would happen more out into the harbor. So he started asking around, and you can see in the upper middle there where the university camera was, looking out towards the harbor. And on the left-hand side, an airplane was landing, a small plane was landing at the Lima airport. The pilot saw the lights, and he knew what direction it was coming from. And the third guy was a soldier down in the island, which is the landmass in the bottom right. And he saw it and was interviewed and said, yeah, I saw it from that direction. When you put all of the vectors together, it showed that the lights actually came from a small island in the middle of the harbor, sort of a rock outcropping. And the artist's rendition here was vertical streams of lights going from the rock upward into the sky. So that's what they saw. They knew it was in the harbor. They knew it was not on land. It wasn't caused by transformers or anything like that. So if we fast forward now to our area, San Francisco Bay Area, back in 1989, there was a large earthquake, a magnitude 7 or 7.1. That was the Loma Prieta earthquake. And some of you may have actually experienced it. It happened during the World Series baseball game up there at Candlestick Park. Unbeknownst to most people, Stanford University, Tony Fraser Smith, had a Navy project where he had a magnetometer in a little town called Corralitos, which was about 6 miles from the epicenter up in the Santa Cruz Mountains. That magnetometer, unbeknownst to even him, was picking up some really large magnetic fluctuations. So the graph that you see there is actually a frequency spectrum down at the 0.01 hertz level. So if you can imagine a sine wave of magnetic fluctuation that takes 100 seconds to go through one complete cycle. It's a very, very low frequency. We call it ultra low frequency magnetic field changes. When he looked at that frequency band, he could see something dramatic starting about 30 times the normal background signal, starting about 12 days before the earthquake, and then getting very quiet, unknowns to him even at the time, for about a week. And then just before the earthquake hit, for 3 hours, this thing went almost off scale, about 60 times the normal background signature. The gap is because the little Macintosh computer fell off the table, ran out of juice. They had to retrieve the hard disk and get it back. And they could see all of these other peaks afterwards. And those peaks are not aftershocks. They're actually peaks of magnetic field changes before the aftershock happens. So that made a lot of press and was written up in a lot of scientific papers, but it was sort of dismissed at the time because it was only one site that had a magnetometer. There wasn't anything that correlated from other magnetometers that could prove that it wasn't just a fluke. So here we have a situation where signals are being generated, they're being recorded. We've seen it in earthquake lights, we've seen it in magnetometers. A guy down here, almost across the street at NASA Ames, a material scientist, not a geologist or anything like that, he was experimenting with granite, trying to see if he could get any electrical activity out of it. Now, this is not piezoelectricity. This is actually something different. So he would take a 9-foot-long slab of granite, kind of like a curb that you see along the side in the parking lot, and he'd squeeze one end of that about halfway to the breaking point. It wouldn't really even crack it. It would just be about halfway. When he did that, he put a copper conductor on the tip of it and hooked it up to an ammeter, and he could actually get a steady state current coming out of the rock. Now, these were nanoamperes, 10 to the minus ninth, but the rock was starting to act like a battery, and current was flowing through the silicon-based rock. Everybody thought rocks were insulators. They wouldn't be able to do that, but it's sort of like a semiconductor effect. Instead of an electric field, stress is the energy source, and it releases small ions from oxygen anions that are ripped away from a lattice boundary and start going through the rock. When you look at something the size of an earthquake fault, you're not talking about 10 or 15 square inches of rock anymore. You're talking about square miles of rock. When you do that and you stress it asymmetrically, you get currents on the order of 100,000 amperes to 1 million amperes. And those were actually measured by measuring the magnetic field changes prior to a large earthquake in Taiwan. So 1 million amperes spurting out of this area causes very, very large magnetic field changes. So I'd like to kind of show you an animation just to get a sense of the timing of everything, because the timing is important here also. So here we have a cutaway of the crust of the Earth. The brittle part is on top, sort of a P wave, a P-type semiconductor, and down at the bottom is a more plastic area, sort of the magma area, an N-type. The red dot in the center represents the hypocenter. That's where the earthquake actually starts, and it zippers out from there, or avalanches out from that high stress point. On the top of the crust of the Earth, we have our magnetometer, and we have some mountains in the background. So I want to show how all of these things interact, and I'll start it now. So we have the observatory, which is a 3-axis induction magnetometer. We have the hypocenter, and we get these pulses of current that create unipolar pulses. Lightning also causes those pulses, but we'll show you those a little bit later and why they're different. So what we want to do is we want to instrument this somehow. And by having a magnetometer on the Earth looking for these magnetic pulses, we can see them, we can record them, and we want to show that they're not continuous. In other words, they pulse out for a short time and then they stop. So we record the pulse on the lower left there, lower right. We get another pulse, we record that, and then these charged particles, the positive ones seem to migrate to the surface, and when they cluster around a rock outcropping, they can actually ionize the air. The voltage gradient at the point of a rock is so large that it ionizes the air. And all of this happens before the earthquake actually snaps. So that sequence of magnetic pulses, air conductivity, and earthquake lights are all happening on the order of 14 days to a couple of hours before the earthquake. Now, being a doubting Thomas, we decided, okay, you got a laboratory indication that there's current, but nature is not nice and clean and dry like a laboratory. We happened to have a 7-ton boulder at a site where we were building a cabin. We had to get rid of that boulder because it was on a hillside and it was ready to kind of roll down right through where the cabin was going to be built. So we had to break it up, and the simplest way to do that is to drill holes into it, 4 of them, about 4 feet deep, pour inside of those holes a concrete mix called Bustar. And it's essentially an expanding concrete. As soon as it starts to dry, it expands dramatically, and it actually breaks the rock from the inside out. At the same time, in the upper left-hand corner, you'll see near my feet are a couple of white tubes. Those are the magnetometers that we laid next to the rock. Across that clothesline on the top of the rock, we put a couple of ion sensors that would sniff for ions. There was a surface charge indicator that picked up by about 3 volts of charge, by the way, on that. And off the camera, where you can't see it, was a $250,000 infrared spectrometer looking at the center of the rock, kind of like a bullseye. And we wanted to see if there was any infrared energy there. The lower left, you'll see some pulses that started up. So we poured the concrete at 10 o'clock at night because we had this infrared thing that had to work at nighttime. At midnight, 2 hours after the rock started to have this concrete expansion, we started to get ions being sniffed by the ion sniffers. And on the lower right, we started to get pulses of magnetic field, indicating that there were currents being generated inside the rock going downward to where it was touching the ground and then essentially grounded out from there. So in a sense, we had created our own miniature earthquake. We had taken a natural rock in its natural setting, broken it slowly over about 8 hours, and 2 hours into it, we generated all of these signals before the rock actually broke, which was like the earthquake. So what does it really look like when you get an earthquake now? Now we're going down 10 miles below the surface, not on the surface. So here's a 30-minute segment of magnetometer, induction magnetometers, which only show the ripple of the magnetic field. You'll see a few oscillations on the lower right there. That's a little burst of magnetic energy from the sun during a solar storm. But just before this earthquake, we started to see these skinny little spikes that were sticking up out of the data. The spikes were about a tenth of a second to 10 seconds long. So they're rather short little things, and they're asymmetric. In other words, they're taller on the top than they are on the bottom. Very unusual in nature. Nature is always balanced. It sort of has a characteristic oscillation that goes both positive and negative. This was more like a spurt. It was spurting up and then decaying down. What happens over 2 years before the earthquake? Do these things happen all the time? Turns out they do. So if you take the Alum Rock earthquake, which was past Milpitas up in the hills on the Calaveras Fault back in 2007, we discovered these same pulses at that time. We looked back in the data 2 years before it occurred, and we got lucky. We had one of our magnetometers about 2 miles from the epicenter, so we were nice and close to it this time. And we saw pulses like 10 or 20 every day all the way through those 2 years. It's like the fault is moving, grinding, slowly bending that fault. But every once in a while it catches and releases, and you get a pulse wave train that might be 150 or so. The trouble is it doesn't stay there. In other words, there wasn't any earthquake there. It was like it caught and released before it could actually zipper or avalanche into an earthquake. On the lower right, in October of 2007, the pulses started getting much more frequent, much higher, much closer together, and we could see this buildup happening just before the earthquake. Same thing happened in Tacna, Peru. So that was one earthquake. This is the second earthquake. As soon as we put the sensor in about a month, we picked up 2 earthquakes up to a magnitude 6.2, but we didn't know what the background signal looked like. So we had to wait the entire summer, and you can see that there's virtually nothing happening all summer until the early fall when the pulses started building up quite high this time. And this was in an area that they were expecting a magnitude 8 earthquake, a really high danger area. Turned out that we had a cluster of about 4 earthquakes happening in close succession. And that's what this precursor set of magnetometer indications seemed to show. So that's magnetometers. We didn't want to put all our eggs in one basket, and we said, what in the physics is happening besides just the magnetic current or the currents? And we said, okay, those charged particles that were migrating through the rock, they were actually measured at 300 meters per second. So not the speed of light, but it was migrating up through the rock to the surface. So we ended up putting a positive and a negative ion sensor, which is nothing more than 2 plates of conductive material, one charged to like 6 volts, the other one at ground. And depending on where the charged particles were, if they were positive, they deflect one way. If they were negative, they deflect the other way. We could count those as they were coming up. And prior to the Alum Rock earthquake, this is 2 weeks on the top plot and 2 weeks on the bottom plot, we started to see little spikes of ion signals going up. There was also some noise in the system when it rained. The sensor got wet and it started to conduct on its own. So where the X's are, that's just noise. But down at the bottom plot on the bottom right, you can see where the earthquake actually happened. And the positive ions that were being monitored actually went off scale 23 hours before the earthquake. And we had never seen anything like that before. The humidity was like 70%, so it couldn't be caused by the wetness of the fog or anything. So now we had a second indicator. The third indicator is what happens to the charged particles when they hit the air. They eventually neutralize in the air because they bump into water molecules or other dry air molecules, and they drop their charge. But the law of conservation of energy says the charge has to go someplace. And what happens is the charge ends up being manifested in a photon of energy in the infrared band. And it turns out that the 11 to 8 micrometer band is the same band that the GOES weather satellite can actually see. So when you look at the news tonight and you watch the clouds coming into the California coast, if you were to actually watch that satellite data at nighttime, not at daytime, there's an infrared camera on there, and they rarely show those images at night. But if you were to look at them, that infrared camera is looking down in California, like Mountain View here, and it's seeing the temperature of the ground go up every single day as the sun comes up, heats the ground, 70, 80, 90 degrees, whatever. Then at nighttime, when the sun goes down, that energy radiates out into cold space, and the temperature of the ground goes down. So you see this characteristic temperature curve, negative slope, in the upper right-hand corner. Before an earthquake, however, that slope starts to go positive. So that says, like in the lower right-hand corner there, where the red dot is the Alum Rock earthquake. The pink and yellow area represents areas where the slope is starting to go either neutral or positive prior to the earthquake. And that phenomenon was picked up by some scientists down at Jet Propulsion Laboratory in Pasadena, and we're now trying to use that same technique. As a matter of fact, here's what it kind of looks like when you look at California. This was in July when there was actually a storm going through Southern California. The gray represents areas where the slope is just normal, it's negative. White means clouds, I can't see through them, so that's like neutral, we don't know what's going on. But the red are areas where we have a positive slope. So you can see the next day on the right, we're getting a little bit more cloud-free area, and there's a few more areas of red. But you have to be careful, because as a cold cloud moves away from warm ground, it looks like it's heating up dramatically. And that is not an earthquake signal. So we use a technique to look at confidence level. Wherever it's sort of red here, it says we got good data. Wherever it's green around that area before the clouds, that's where you don't basically trust it. So that being said, what is it that we're looking for? And it's really a pattern, a time pattern of all three indicators: magnetic pulses in black, ion sensor indications in blue, and infrared indicators in red on this. So we put them all on one plot before the Alum Rock earthquake, and you can see that it built up 2 weeks before the earthquake, all three of them at the same time. Then there was about 1 week of quiet, and then another peak just before the earthquake. And if you remember what we were showing before with the Tony Fraser Smith data, this is just magnetometer data on the top. He had the same pattern. 2 weeks or 12 days before, it got up really high for about 4 or 5 days, a quiet period, and then a pulse just before the earthquake. And they line up pretty close within a day or two of what we saw at Alum Rock. So we've seen about 7 or 8 more of these through other earthquakes. The trick is you got to be in the right place at the right time, because the magnetometers are trying to pick up a signal that's 10 miles below the surface of the ground. Those large currents that are going out dissipate very quickly. You can't hear them more than about 10 or 15 miles away. And the result is that you have to have a sensor about every 20 miles. So what we've done over the last 13 years is to put out 130 sensors in California, all the way along the San Andreas Fault from Eureka to the Mexican border, the Calaveras, the Hayward Fault, the Garlock Fault, San Jacinto. All of those major faults now have magnetometers and air conductivity sensors. And then we went overseas because we didn't get enough earthquakes in California. I mean, we need more data. And we're the only guys that want more earthquakes in California. Not by my house, but someplace close there. And we'd like to get more samples. So we put them in places like Taiwan, which has 15 times the number of earthquakes that California does. Peru had a couple of magnitude 8s. Greece had some large earthquakes in the Corinth area. So what we've got now is we've got a theory, we've got some data, we've got a pattern we're looking for. We'd like to move from the laboratory and the research actually to operations. We'd actually like to start making real-time forecasts. And if you guys have ever gone through a software development cycle, it's usually The first part of it is pretty easy. You thought the basic idea, but by the time you make it usable for the general public, it takes a heck of a lot more work and refinement. That's the phase that we're in right now. We have 4 things that are technical challenges up on the top and 2 programmatic challenges, which are on the bottom here. So we're going to look at them real quick. Lightning. As you saw in that animation, a lightning strike above ground looks a lot like the underground strike, and we don't want to count those because that's a false alarm, and we get killed if we had lots of false alarms. So how do we know that this is lightning and not an earthquake going? What we did is we partnered with a company called Earth Networks, who actually publishes all of the lightning strikes in the United States, actually worldwide. And each one of these little red crosses here is a lightning strike, documented by the time of the strike, the location of the strike, and the magnitude of the strike, and actually the direction too. And what we can do is take one of our sites and look at it and see if there's any lightning within 100 to 200 miles of it. Look at the time of the lightning strike, look at the time of the magnetic pulse. If they're coincident within half a second, that means it's lightning and we throw it out. If there's no lightning and we see a lot of pulses, unipolar pulses, then it's from underground. Likewise, man is noisy. I don't know if you've ever looked down the street here as the cars go by, but we can see a car drive by 300 feet away from one of these magnetometers because it deflects the Earth's magnetic field. But that we can deal with pretty easily. It's BART. BART is a killer for us. Every time a BART train starts up, it draws about 10,000 amps into a big electric traction motor, and that pulse of current is amplified by 140 miles of track. So, for example, on the left-hand side, we have a site at my house in Portola Valley, which is just down the road here, west of Stanford, up in the hills. Pretty quiet. All 3 magnetometers are well behaved, and we can see 20 pulses a day going through there. On the right-hand side is Richmond, California, across the bay, and that's within about 2 miles of a BART station. So at midnight to 3 a.m., the BART trains are in the barn getting maintained. From 3 o'clock all the way through the rest of the startup cycle in the day, the work cycle, they're going back and forth across multiple tracks, and you can see the amount of noise that's generated. So that's a challenge that we still have to handle. Luckily, outside of the Bay Area, and even some places in the Bay Area, we get clean data. It's just along the Hayward and Calaveras Fault that we have problems. Likewise, the air conductivity. You guys have bugs in your software. I have bugs in my hardware, and I really mean real bugs. I mean, they're spiders. They think these air conductivity sensors are nice and warm and cozy in the cold wintertime. They'll crawl up inside of it. They'll start spinning their web, and every web is a nice conductor across the plates. So we've had to go in there and put stainless steel screens on it, really fine screens to keep them out. We've gone to stainless steel to get rid of some of the static electricity, and we've coated all of the circuit boards with silicone because we don't want moisture to get in there. So these are things that we can do. But now we're at a point where we're trying to push ourselves into forecasting these earthquakes. And I think the thing that'll increase our credibility is if we actually do forecast 3 earthquakes before they happen. So if you do 1, they say you're lucky. If you do 2, you're just really lucky. If you do 3, you know, you got a trend going here, and there's something to this. So we put as our goal for the next 5 years is to predict 3 earthquakes somewhere in the world where we have our sensors. The other thing is that we just got to communicate what the heck we're doing to the outside world. And quite honestly, we're not really good at that. We have a website. We show all of our data on the website. Every station that you saw on that map, you can go to the website and click on it and actually see the data. So if you know where your house is relative to one of these sites, you can actually look it up. But just communicating that to the general public is something that we're not very good at. I'm winding up now, but I did want to stop and just give a special thanks to Google Earth, because that is one of the greatest tools that we've ever used in our research, because we're trying to position all 200 of these magnetometers in areas that follow the fault every 20 miles, within 1 mile of the fault, and in a quiet location. So we can actually go into a nice rural area, go down a cul-de-sac by Google Earth, find a house that would be really good. We can even tell the guy what part of his lot we think we ought to put this thing on, because we can see where he's got equipment and horses and tractors and stuff like that, and just pick a spot. So by the time we go to the guy's house, knock on his door, ask him if we can use his property, we already know where we want to put it. And 50% of the time they'll say, oh yeah, this sounds really cool. Go ahead, stick it in my backyard. So finally, getting involved. This has been a collaboration between Stellar Solutions and our small team of about 5 people, a number of universities, a little bit of NASA help. We've gotten a little help from Tesla, from PG&E, Telefonica, Vodafone. But this is sort of a community upswelling of interest that we think we're starting. We're trying to find more sponsors, people that can help us get these sensors out faster. That takes money, unfortunately. And, you know, we need help getting the word out, too. We need help with our website and our way of publicizing this thing. We also need technical help in the algorithms. So we kind of throw that out to the general audience. If anybody is really intrigued by this and wants to get in touch with us, there's my name and phone number and email address. I can give you a card after this if you'd like. So I think at that point we're pretty much done. I would like to open it up to questions, maybe for 10, 15 minutes, depending how much time you guys got. So, okay. So, you okay?
I have a microphone here. If anybody has any questions.
Oh, we got a couple in the back there.
Hello? Is this working? I'm just checking. Yeah.
There we go.
Okay. I'm sorry.
Thank you for the amazing talk. My question is about, do you have any indication of the magnitude of the earthquake? And do you have like a lower bound of earthquake that you can detect?
Really good question. We definitely have a lower bound for the earthquakes, because these signals do originate, you know, miles below the surface. And it seems like the smaller earthquakes have some smaller currents. So we've, by empirical analysis, just looking at examples of earthquakes, we think a magnitude 5 is about the threshold. But that's about the time where you start to get damage. You know, when you get to a 6, things start to fall apart, and 7, you really got damage. So we cannot predict 3s, 4s. You might get a 4.8 if you're close. And relative to magnitude, we've only had about 8 good examples so far. I think we're only about halfway there on doing magnitude. We think we can get the time within about 24 to 48 hours. We can get the location to within 10 miles of the closest site that has the biggest signal, you know. And the magnitude, we're not sure if a magnitude 7 or 8 will just have a lot more pulses, a lot taller pulses, because we've never had a magnitude 7 that we picked up. We're up to about a 6.2 is the largest one that we've had so far. So the fact that it's over a magnitude 5, we can kind of get an indication. When we have a cluster of earthquakes, it seems to last longer. The pulses last longer. We don't know what a magnitude 7 looks like yet. So we'd like to get one of those, but again, not too close here. I think we had another question in the back. Same question, okay. Anybody else?
So, like if I want to keep track, like, oh, what are the signals looking like? Or, I mean, how can I see your website, but like, how can I tell, like, Tom is thinking, so, hey, watch out if you're in wherever. I mean, are y'all putting this out, or is it kind of between you? Or?
Well, We're in a research phase yet, so we've got to be careful what we put
Sure.
out, number one. There's also a law on the books that says we can't go to the press and say there's a huge earthquake coming.
Got it.
So we work through USGS and we work through the California Emergency Management Area. And there's a bunch of scientists that banded together called California Earthquake Prediction Evaluation Council that would look at it. And while we're doing the research, we would send our predictions through them, and they would vet it. They would look at it to see if it makes sense. But the raw data, the process data is on the website. When you go there, there's a data tab on the upper middle of the website. It'll ask you to just register. Just give us, your email address, and you can put in a password. We just sort of keep track of how many people are coming to the data part. But then you have access to essentially all, 150 of these sites, overseas as well as California. Pick out the one closest to your house and just watch it every day if you want to, and you can see what's going on.
Okay, so I have a question then too with the data. Like if it goes to the committee and then they vet it, then where is it? Where would a person see that or hear about that?
We haven't yet done that yet. We haven't made our first prediction, but I think the sequence is it would go to a group down in Southern California. It ended up going to the CPEC group. They would make a recommendation to the governor through CalEMA. So you've already seen 3 steps that we have to go through. I don't know how long that's going to take, by the way. It may take longer than the earthquake forecast is, but theoretically it would go through CalEMA to the governor, and then the governor would actually indicate that he's officially putting out an earthquake warning.
Got it.
So, there may be like a yellow and an orange and a red type of thing as you get closer and closer to the earthquake. That's what we sort of see as the operations concept as we go through the pulses, the quiet period, the IR, and the ions coming up. But the hope is that you'd have about 24 hours. You'd say 24 to 48 hours from now in this site in Mountain View versus this site down in Southern California, you're at a much higher risk for an earthquake greater than magnitude 5. Now, what would you do? I mean, I don't know about you, but I'd probably still go to work. I'd still do that. But, I'd have my emergency supplies of water and fuel and food that I needed. Have sneakers in my car in case I had to walk home. If I had kids, I might keep a really short leash on my kids. I know where they are. All of these things that kind of came to my head in 1989 when we had that big earthquake and my kids were out at soccer practices and everybody's house, and it was hard to get them all back at the time. I would probably do things differently if I knew I was in a high-risk time period, like 24 hours. Yeah. Anything else in the back there?
Thanks for the great talk. Is there any work going on putting these sensors under the sea? Because the North Anatolian fault line, the expected Istanbul earthquake is supposedly happened under Marmara Sea, and probably it's going to be hard to track those fault lines under the sea.
Yeah, we haven't figured out how to put these things underwater yet. Interestingly enough, the earthquake lights have been seen coming out of seawater, not only in Lima, Peru, but in many other areas. So you wouldn't think that they would go through conductive water all of that easily, but they do. The ground underneath us has got a lot of salt water in it too, and it does go through that. I think it's just a practical problem of encapsulating this thing so that it's watertight at the depth that the thing is. And we're getting 60 megabytes of data per day out of each site. So we're not doing kilobits, we're doing megabits, and that's really hard to get it out of the undersea applications. But we talked to some folks in Turkey about the Anatolian Fault and recommended that we put them along the ground-based Anatolian Fault for a number of miles, and that's just sort of sputtering along right now. But there's a few people that are interested there. Yeah. Anything else?
One sec.
Is QuakeFinder or any other interested body trying to make correlations or associations between this electromagnetic phenomena you've described and the known behavior of animals going missing before an earthquake?
Yeah, yeah. As a matter of fact, we have a project that's just starting up now. You remember the big Sumatran earthquake where the tidal waves came in there and tsunami rather and killed all of those people. There were anecdotal stories of elephants running away from the shore before that all happened, birds flying off, all sorts of animal behavior going on there. One of the guys in the Red Bull company, you know, the energy drink, he lost a close friend there, and he approached the scientists in Vienna about doing an animal research project on one of the islands just off the coast of Sumatra. And he came to us and said, gee, you know, there's lots of stories, actually lots of reports about animals that have been documented. It would be interesting to put your magnetometer and air conductivity sensor in the same complex, and they're actually going to instrument animals. I don't know how they're going to do this yet, but, you know, fish jumping around in a tank, birds flying around in a cage. They're going to instrument these things and plot how they react. And they hope to have a fairly large earthquake, you know, within a few years. We'll have one of our magnetometers right next to them to see if we see those same indications prior to that. And if you think about it, the fact that we got these extraordinary number of ions coming out of the ground before Alum Rock, if you were a dog sitting on the ground or laying down on the ground, and that amount of charged particles were coming out of the ground, your fur would probably stand out on end, just like static electricity hitting a Van de Graaff generator. Maybe that's what they're picking up. You know, it's very possible that that's not normal for their fur to be standing out. Some other guys have actually put animals in a cage and generated ultra low frequency magnetic fields, and they got them to react to that too. So animals are pretty sensitive. I mean, they use magnetic fields for navigating, birds do. They can sense things much better than humans can. So there may be a definite connection. I can't say that for sure, but it kind of makes sense to me that they would feel it.
Is there any reason to think that their earthquake activity might be correlated with events off the planet Earth, say with the activity on the sun?
Storm?
Or just the larger solar system?
I think there have been a few studies about major solar storms, whether or not that triggers an earthquake. And it hasn't shown very much positive result. I mean, from a worldwide standpoint, you can look at the number of earthquakes per day, and there's a lot of them, 10,000, you know. We just had a big solar storm the other week, last week I think it was, where they saw northern lights in Minnesota. There was no big flurry of earthquakes going on at the time. So if there is a trigger, it's really subtle, and it's not something that has shown big correlations yet. Yeah. Yeah. Gopal?
Yeah, so far, have you seen a lot of false positives on the recordings that you've gotten? And how are you actually deciding when an earthquake's going to happen? Is it just a threshold? Do you have some sort of probabilistic model to assess a probability?
Good question, because yes, there are a lot of noise out there, and we kind of addressed some of them. I think lightning was the biggest one because it actually has the same shape as the underground earthquake thing. Lightning is a little bit faster though. It's about 1/10 of a second strike unless you get multiple strikes. The pulses that we're looking at are about 2/10 of a second to maybe up to 10 seconds long. They have a slightly different shape to them. So it's a little tricky to weed through all of that chaff and see those. Solar storms, when we see those, they have a very characteristic wiggle pattern. We can actually filter those out with MATLAB using low frequency filters on it. The cars going by when they're close enough, they have a very characteristic balanced type of pulse that we can get out. But a lot of it is setting thresholds, eliminating lightning, eliminating solar storm data. So you kind of subtract all of these things that you know of, and then whatever is left over, it flags it to us in our software, and then the human being looks at it from that point. Because occasionally somebody will park a tractor right next to our system or start a welding a fence near us. And that looks very different than the earthquake signal. So are we there yet in the sophistication on the algorithms? No. We need more help, more refinement. So we're in the tuning phase right now. But yeah.
So have you had a situation where you thought an earthquake was going to happen and it didn't happen?
We actually made one forecast. Actually, our partner down in Peru did when we had that cluster of 4 earthquakes in Tacna. After the second one, he sent an email to the rector of the university saying, I think there's going to be another earthquake in that same area. And there was. It was like putting your toe in the water. We just gently did that, tried it once. The other ones that we've had in California and Greece, we haven't really pulled the trigger on them yet because we didn't feel that our algorithms were quite tuned up enough. And we're really afraid of doing too many false alarms because that's crying wolf and people will just lose confidence. So we'd rather take a little bit slower, make sure that the algorithms are moving, and hopefully we'll be close to a really big earthquake where it won't be down in that noise, it'll just be booming. And hopefully we'll get a couple of big ones that will be very evident. So we're not there yet.
So based on historical records, how much data do you expect to collect in the next 10, let's say next 5 years?
I can tell you where we are now. I think we're at about 24 terabytes.
I mean, in terms of numbers of earthquakes that you can then try to correlate against.
Yeah, it's
train algorithms.
well, now that we have more sensors out, which took us 13 years to get there, we think that we'll hit most of the big California earthquakes. How fast do you think the earthquakes in California are going to happen? I mean, I don't know. We're in a cycle now where Hayward is actually has a repeat cycle of every 140 years on the Hayward fault, and we're at about, I think, 145 right now, and it's 140 plus or minus 20. So we're in that sweet spot. The San Andreas fault that goes through here happened in 1906, and I think that's about a 100 to 150 year cycle. So we're kind of getting close to that sweet spot. But you just got to be there, and you have to have, a year or two of data to make sure you understand what the noise environment is. So probably ought to wind it up pretty soon, but last licks, last question.
Are there any more questions?
Very good.
All right,
Thank you
well, let's
guys for
thank
showing up.
Tom.
Appreciate it.
Wonderful talk.
Yeah.